So let's see here. There we go. All right, Chemistry 3101. We completed the section on infrared spectroscopy yesterday, and now we're into mass spectrometry. So again, spectroscopy was the study of the interaction between light and matter, or electromagnetic radiation and matter. And now we're going to talk about mass spectrometry, which is the interaction between energy and matter. So here's our introduction to mass spectrometry. And if you remember, infrared spectroscopy was used to determine functional groups. Is this a carboxylic acid? Is it an aldehyde, a ketone, an ester, an alcohol, etc.? Primary, secondary, amine, all that good stuff. Well, mass spectrometry, its utility is to determine the molar mass and formula of a compound. And so if you know the functional groups, if you know the molar mass, then you're getting closer to determining the structure of a molecule. So what do we do in mass spectrometry? It says the first thing we do is we vaporize a compound. So that means we put it into the gaseous phase. That means even if it's a solid, we put it into the gaseous phase. If it's a liquid, we put it into the gaseous phase. And if you're wondering, well, if it's a solid, how do I put it in the gaseous phase? The way that that's done is by obviously subjecting it to heat, but then a low pressure too. So it goes into a vacuum chamber and it gets heated up, gets converted into a gas, and then it gets ionized. And we're going to talk about ions a lot in this chapter. And then it undergoes something called fragmentation. And I'm going to explain to you some fragmentations that you need to know as a Chemistry 3101 student. And then, like I said, the word ions is going to come up a lot. The masses of the ions are detected in graphs. So let me just park it right here for a second. A couple things I want to go over with you. Number one is I want you to really focus in on this word here, okay? The only thing that we see graphed in a mass spectrum are ions, nothing else. If it doesn't have a charge, it doesn't show up in a mass spectrum. So what shows up in a mass spectrum? Ions are what shows up in a mass spectrum. Now, another thing is if you've read the entire chapter from soup to nuts, and I always have students who do that, you'll see that there's a section which is 14.13. We skipped that section, and that deals with high resolution mass spectrometry. And that's where we look at the masses of the elements and we give them all kinds of decimal places, all kinds of sig figs. However, what we cover in Chemistry 3101, I'm going to write it down here for you. Chemistry 3101, the kind of mass spectrometry that we do in this class, okay, is what they call low resolution. So write this down, okay? In Chemistry 3101, we study low resolution mass spectrometry, no exceptions to that. If you're in Mr. Geiger's lab course right now, and he's talking about mass spectrometry, it would be the same thing. We only talk about low resolution. And so what's pertinent about low resolution mass spectrometry to you is that we only look at the masses of the elements to the ones place. And so I'm going to scribble them down and I want you to write them down. So for hydrogen, we give it a mass of 1 AMU or 1 gram per mole. I'm just going to leave the units out right now. We're going to say hydrogen has a mass of 1, carbon has a mass of 12, nitrogen has a mass of 14, oxygen has a mass of 16. Then we look at 2 of the halogens every once in a while. Chlorine has a mass of 35. Bromine has a mass of 79. And then one that's a bit of an outlier that shows up maybe once in a while is sulfur. Sulfur has a mass of 32. And those are the main ones that we're going to look at. I guess iodine has a mass of 127. That might show up here and there. But again, these are the masses that I'm going to use for the elements. Okay, you with me on that? Those are the masses I'm going to be using in this chapter. So let's say we had something like, I don't know, something simple. Let's say we had a molecular formula like C5. Let's just pick, I don't know, write it down here. C5H12, something like that. So what you would do is you would say that what's the mass of this compound? Well, you'd calculate it using these low resolution masses. So you'd say 5 times 12 for the mass of the carbon. So 5 times 12 gives us 60. And then you would add 12 times 1 for the hydrogen. And that would give you a mass of 72. So give me a thumbs up if you follow me on that. We're going to use low resolution Mass spectrometry is the only thing we're going to talk about, and we're going to use these masses to the ones place. So don't worry about any decimals whatsoever. All right, cool. Now that we've got that out of the way, let's talk a little bit more about these ions, because if you just look at a molecule like C5H12, well, that's not an ion, is it? No, it's not. So how do we make an ion? Well, it's a great question. It says the most common method of ionizing molecules is by using electron impact, and it's exactly like it sounds, okay? You literally hit the molecule with a high energy beam of electrons. You just smack it with some electrons. And it says here that the sample is bombarded with these electrons that have an energy of somewhere around 1600 kilocalories per mole or 70 electron volts. I'm never going to ask you to remember those numbers that I have underlined. The idea is that they have a lot of energy. So get this. What happens is, let's say you take a neutral molecule like this one here, okay? And of course, they've drawn these carbons in for instructional purposes, okay, to kind of illustrate a point. So you hit it with this high energy beam of electrons, and what that does is it hits it so hard that, okay, it knocks an electron off. So you end up with a free electron, and then you end up with a radical cation. Now, what if you're sitting there going, what's a radical cation, Mr. Dion? Well, hopefully you remember from Gen Chem 1 that a radical just means we have an unpaired electron. So unpaired electron, right? In here, everything was perfectly paired up, but now we have an unpaired electron, so that's a radical. And then a cation, well, if you lost an electron is -1, so that means you're going to have a cation. And of course, it's not stable, and that's why they have it in these kind of square brackets here, right? Because now this thing can undergo what we call fragmentation. So again, what do we see in the mass spectrum? We see ions in the mass spectrum, okay? If it doesn't have a charge, we don't see it in the mass spectrum. All right, so we've hit our molecule with a high energy beam of electrons, we get a radical cation. Let's talk about that radical cation a little more. Now, the next point is that it says the mass of the radical cation is the same as the parent compound. If you're wondering, what's a parent compound, Mr. Dion? This would be the parent compound, okay? The original molecule you're starting with. If you knock off one measly electron, it's going to have the same mass as it did before, right? This is going to have the same mass as this. Why can you make that assumption? Because an electron is so light. If you go back to your Gen Chem 1 days, you might remember that an electron is about, 1,800 times lighter than a proton or a neutron. So when you lose that electron, it's like it has no effect, okay? So we make our radical cation. The radical cation has the same mass as the parent. And it says here, if the radical cation remains intact, it's known as the molecular ion, and we give it this little symbol here, okay? We give it a little M, so that's a capital M, okay? And then we put a plus because it's got a positive charge, right? It lost an electron. And we put a little dot up here to let the reader know it's a radical cation. It's not a cation like a sodium cation or a potassium cation. This is an organic molecule that just lost one electron, and now it's a radical cation. There you go. So let's move on from there. So again, this would be our parent ion, okay? This would be the mass of the parent, okay? It just lost one electron. One electron doesn't have that much of an effect, so we call this the parent ion. And if you're like, oh, I'm not sure about this 100%, well, don't worry. The more we look at it, the more it's going to start to crystallize in your mind. So I'm going to ask you a question. Could you answer in the chat or unmute your mic? Could anybody tell me, what do we detect in the mass spectrum? What is the only thing that we can see in a mass spectrum? And it's not a trick question. I've said it like 3 or 4 times. Thanks. Exactly. Everybody's like typing it in. The answer is ions, right? You're 100% correct. Okay, so I want that in your mind's eye as we switch slides, okay? Because what's going to happen is that radical cation, our parent ion, is not going to be stable, and it's going to undergo a fragmentation. It's going to fragment or break apart into a radical and a cation, okay? So here you have this fishhook arrow. We don't cover those until chapter 10. You see them in this chapter. Don't stress about it. Don't worry about it. I'm not going to make you draw them on the quiz. But when you have one barb on your arrow, it just represents the flow of one electron. Okay, so this electron is going onto the carbon on the left. So we end up with a radical that we see here on the left, okay? And then we end up with a carbocation. Now, again, and you're probably going to get frustrated with me. But out of these two things here, the radical and the carbocation, which one of these am I going to see in the mass spectrum? And it's not a trick. The carbocation, right? That's exactly what we're going to see. Okay, we're not going to see the radical. That's not going to be found in the mass spectrum. The only thing we're going to see in our mass spectrum is an ion. So we're going to see this carbocation. Okay, good. Now, if you're wondering, well, how does it graph carbocations or ions that have different masses? That's a great question. They're deflected by the magnetic field, and they're plotted according to their mass to charge ratio. So the whole idea of being deflected, okay? There's a little picture. I don't think I have it in my slides, but there's a picture in the textbook. Let me just tell you what figure it is. Just let me look here. It's figure 14.21. So if you look at figure, let me just get my blue pen here. Figure 14.21. All right, that shows you a picture of a schematic of a mass spectrometer. And the idea is that if the ions are being deflected by a magnetic field, the lighter the fragment is, the more it's going to be deflected. That's all it means, okay? The heavier it is, it's going to be deflected less. And so that's how we get a graph of them. The second thing I want to address is that they're graphed by their mass to charge ratio. Where's my green highlighter? Their mass to charge ratio. So if you're like, well, what's the, what are the charges that we're going to see, okay? Because we plot it as mass to charge, okay? So we say M over Z. So M is obviously mass, and then we divide it by the charge. Okay, you ready? Here's the answer for charge. Charge in chemistry 3101, I'll put here, I'll even write it out here. Charge in chem 3101 is always +1. And if you're thinking, well, that's good, all I have to do is divide by the number 1. So I just take the number at face value. You're exactly right. Okay, so the Z is always going to be +1. So you just divide the mass by +1. And if you're thinking, well, I don't even need to do that, you're right, you don't. Could you have a mass of, a charge of +2 and stuff like that? Yes, it's never, ever, ever looked at in this class. Mr. Geiger wouldn't cover it in the lab either, so don't stress about it one bit. So we get ions, they're deflected by a magnetic field. The lighter they are, the more they're deflected, the heavier they are, the less they're deflected, and that gives us a spectrum. And then they're plotted according to their mass to charge. Everything that we're going to see is going to have a charge of +1. Thank you very much. Let's move on from there. So here's a mass spectrum, right? Here are some different masses for a molecule of methane. So methane is the simplest possible organic molecule. This is not a trick question. I'm just wondering, could anybody tell me what the mass of methane is, CH4, using our low resolution masses? Yep, exactly. It's 16, right? We have 1 carbon, so 1 times 12, and then we have 4 hydrogens, so 4 times 1, right? And like Sean said, that gives us 16. So if we knock 1 electron off of the methane molecule, it's still going to have a mass of 16, right? Because the electron is inconsequential. So if I look at the masses here on the y-axis, so here's 15, 16, 17, 18, 19, 20, something like that. So you see that the tallest peak in here represents the parent ion, doesn't it, right? This thing here is 16. Okay, you with me on this? This is mass over charge, which is what we see on the x-axis, is equal to 16. Give me a thumbs up if you're with me on that, or stop me if you have a question. Everybody with me on that? Okay, I'm just trying to kind of take it slow to introduce the concepts here. And if you're wondering, well, Mr. Dion, I'd like to ask you, what is this? What is this? What is this? What is this? And what is this? A great question. We're going to try to address that a little bit. But right now, we just want to address the parent ion for the methane molecule. So it says here, the base peak is the tallest peak in the spectrum and is the most abundant fragment. Anyhow, this is a definition you need to know. The base peak is the tallest piece. The base peak is the tallest peak, and it's the most abundant fragment in the whole spectrum. Okay, so the tallest peak here is the parent ion, and we call that the base peak. Now, if you read the textbook before coming to class today, you would know that the base peak is not always the parent, okay? Now for methane, yeah, it just happens to be that the base peak is the parent, but we'll see many, many examples. In fact, that molecule that I drew earlier today, remember this? We drew pentane and we calculated its molar mass. Well, its base peak is not the parent ion, okay? So it's not always the parent that is the base peak. All right. Well, let's move on from there and let's talk about those fragments. Let's talk about some of those other masses, right? We're going to address what is this thing here, right? What is this that has a mass over charge that's equal to 15? Where did that come from, right? Great question. So remember I told you that the parent ion can undergo fragmentation, right? It's unstable, so it's trying to stabilize itself. And so what can happen is you take your methane molecule, okay? We'll draw a methane molecule. And then we hit it with a high energy beam of electrons. We'll put high energy, we'll put here electron beam, okay? And then we smack it so hard that we knock off an electron and we make a radical cation, right? What you're seeing here in the brackets, this is a radical cation. And that is the parent ion, isn't it, right? This is the molecular ion. This is the M plus, okay? Now, what's going to happen is you're going to lose a hydrogen radical, okay? And this is just one of the possibilities here. And then you end up with this CH3 carbocation. Well, that's going to have a mass of 15. And so that is where the mass over charge of 15, that's where it comes from. And then what's going to happen is this thing can lose more hydrogen radicals, and that's what's going to produce the masses at 12, 13, and 14. So if we go back here, right, this mass over charge of 15 comes from this CH3, or this methyl radical is what it is. And then if it keeps losing hydrogen radicals, you get all these lower masses here, which you can see have very low abundances, right? There's not a whole lot of those because abundance is plotted on the y-axis, right? How many of these do we have? And then we have our mass over charge on the x-axis. So before we move on, I just want to address one thing, is that once we start looking at more complex mass spectra, you know, sometimes students will just really get bogged down with it, and they'll say, well, do I have to analyze every single peak that I see? And the answer is no. It's just like in the IR. You have to train your eye to recognize what is the most important fragments or what's the most important peaks for you. Again, same thing in the IR. Which absorbances are the most important to you as a Chemistry 3101 student? How do you figure that out? Really with practice. Study and practice is the only way to master the subject. Let's take just a quick break here and talk about, you know, what is mass spectrometry used for? And there are lots and lots of uses. It says here, mass spec is a relatively sensitive analytical method. So since it's so sensitive, it can be used to determine, you know, metabolites in, you know, in body tissues and fluids and things like that. And so mass spec is used all the time to determine whether people have, you know, certain kind of narcotics in their system or whatever. You know, if you've ever heard of an autopsy being done and they said, well, this person had, you know, Xanax in their blood. Well, that's how they would determine it, is by mass spec. But what I used mass spec for most of my adult life is I worked in the pharmaceutical industry, and I used it all the time for monitoring reactions is what I used it for. So if you've taken the Chemistry 3102 lab already, maybe you've done something called TLC. So TLC is a very useful technique for monitoring a reaction, but mass spec is also a really powerful tool for doing that. We also used it for monitoring different drug metabolites. So again, we'd analyze body tissues of, you know, a mouse or a rat or a monkey or whatever, and then we would be able to determine the structure of different metabolites. What else? Biotech, then we got clinical, we've got environmental, okay? There's a couple of people at UCCS that are interested in environmental chemistry. So if you've ever heard of people, you know, looking into the levels of toxins in water and things like that, so that would be a good, you know, reason to use mass spectrometry. Would be looking at the quality of water, drug testing, like I said. Okay. What else? Geological forensics. There's just a whole holy host of places that you can use mass spec. And so something that I said before I started recording the lecture this morning is, if you're interested in mass spec, or if you're talented with mass spec, it's kind of a joke. I'm being kind of silly here, but you'll always find employment. There's lots of opportunity for people who are good at mass spectrometry. So let's move on from there into section 14.9, where we're going to talk a little bit more about that base peak or that parent ion. And you'll notice that it's kind of written differently here, right? They put it here, they put the M in the brackets and then they put plus, and then earlier they had written it like this, okay? It means the exact same thing, and then sometimes they don't even put brackets around it. So I'll probably use a mishmash of them, just like the book does. So if we look at this compound, this is benzene. It's C6H6. So if we calculate the mass of benzene, could anybody tell me what it would be? Could anybody do that one in their head? And it's not meant to be a mind boggler or anything. It's just kind of a, yeah, thanks, Sean. Exactly. So Sean says you get 6 times 12, right? That gives you 72. Plus you've got 6 times 1 for the hydrogen, so that gives you 78. Oops, I don't know why I wrote 73. And yes, you've got 78. Look at this, Sean. If you look at the mass spec, so we have 75, 76, 77, 78. What do you know? So the molecular ion here, the parent, happens to be 78. Okay, so that's the parent. And you could also say its mass over charge is equal to 78. It means the exact same thing. Okay, there's our parent. And it just happens that the base peak, right, which is the tallest peak, so remember base peak is tallest peak, okay, is the same as the parent for benzene. Why? Because benzene is a very stable molecule. I'm just going to scribble this down here. Very stable molecule benzene is, okay? Very stable molecule. And we'll actually talk about the stability of benzene a lot in organic chemistry too. And so the take-home message here is that the parent ion, the molecular ion, it actually doesn't fragment all that well. Yeah, I know there's fragments. There's some here and here and here. But man, I'm telling you, once you start looking at other mass spec, you're going to see that this one doesn't have a lot of fragments. There just isn't an abundance of them here. So let's turn our attention to something that has more fragments. Want to do it? Let's do it. Let's go to the next slide, and we're looking at a pentane molecule. So this is pentane, and we already determined earlier on that pentane is C5H12, so this has a mass overcharge that would be equal to 72. And if you look for the molecular ion, we have 70, 71, 72. So there's the parent, which has a mass overcharge equal to 72. But you can see it's definitely not the base peak, is it? Does anybody have the slides printed out or have them on their computer? Could anybody identify the parent, or sorry, the base peak here, what the mass of the base peak is? Can anybody? Yeah, thanks, Sarah. You're absolutely right. Yeah, Sarah says right here that this is the base peak. So base peak, okay, has a mass overcharge that's equal to 43. There you go. So that's the mass of the base peak. But when we're talking about fragmentation, what we want to know is how much mass did it lose? Okay, what did it lose in order to have a mass of 43? So if we take 72 and we subtract 43 from it, what do we get? So let's just do a little math here. If we do 72 minus 43, we get 29. Okay, so what the idea is this, and you're gonna have to pay, if you're not paying attention, put down whatever you're doing and pay close attention to me right now. Okay, so if we go from the parent all the way down to the base peak like this, what did it lose? What happened was we have the parent ion, and then it lost 29. Okay, that's where we got 43, right? It had to lose 29. Now, if you're like, what has a mass of 29? 29 equals, I don't know. What has a mass of 29? Well, I'm actually going to show you what has a mass of 29 in a couple of seconds, okay? So we're going to get into that in a little bit. If you look at the mass spectrum, you'll also notice that there's a peak at 29. But anyhow, let's see, what else do we have here? We have another peak here. This one has a mass of what? If we take 55, 56, 57. So this one here has a mass overcharge that's equal to 57. So how much did we have to lose to go from here to here? 72 to 57. Anybody can do that math in their head? It's m minus what? How much did the 72 have to lose to give you 57? 72 subtract what gives you 57? Yeah, the answer is 15, okay? So that means that this is m minus 15, all right? Now you're probably wondering, well, what has a mass of 15? It's like, what has a mass of 15? Well, we're gonna get into that in just a second, okay? I just wanna put that bug in your ear and just kind of show you how we start analyzing a mass spectrum. So let's just talk about that parent ion, and I wanna introduce you to a rule on this slide, okay? The main rule that I want you to know on this slide is something called the nitrogen rule. Okay, let's see here. It's these two things here. This is called the nitrogen rule. Okay, everybody who's taking this class needs to know the nitrogen rule. Okay, let's back up just a half a step here. Whenever you're looking at a mass spectrum, the first thing you're going to do is look at the radical cation, right? You're going to look at the parent. Okay, it's not necessarily the base peak. It might be, like in benzene. It might not be, like in pentane. Depends on the molecule. Okay, now it says here, if the mass over charge of the parent, the mass over charge of the parent is equal to the molar mass of the compound. Okay, so all it's saying is that this is equal to the molar mass of the parent. Molar mass. Nothing. I'm pretty sure you had that figured out already. Okay, so then here's the nitrogen rule, and this again, you got to know the nitrogen rule. If you have an odd mass for your parent, it means there's an odd number of nitrogen atoms in the molecule. Okay, an odd mass means that there is an odd number of nitrogen atoms in the molecule. Nothing more than that. Odd mass, odd number of nitrogens. The other version, or the second part of it, is if you have an even mass, it generally indicates that you've got no nitrogen, so absence of nitrogen, or you've got an even number of nitrogen atoms present in the compound. So let's take a look. Let's start in the middle. Okay, if we look at this molecule here, this is called butanamine. The name isn't here nor there because we don't learn amine nomenclature until organic 2. But the idea is that it's got one nitrogen in the molecule, so it has an odd number of nitrogens, therefore it has an odd mass. If you look at the other two compounds, so if you look at pentane, it's got no nitrogens, and this one here, which is a diamine, this would be 1,3-propane diamine. Again, name's not important, but it's got an even number of nitrogens, so it has an even mass. But again, the nitrogen rule, usually what my students just kind of hitch their wagon to is this. If you have an odd number of nitrogens, you get an odd mass. That's the end of it. There you go. Give me a thumbs up if you're with me on the nitrogen rule. You got to love that nitrogen rule. I mean, what are some favorite rules that we have? I don't know. Nitrogen rule, maybe? All right, let's move on from there. Okay. Let's see here. If you're very astute, and I know that every one of you is, you probably noticed that in the mass spectrum of methane, which is the simplest possible organic compound, right? We already identified the molecular ion. Okay, this is our parent ion here, which is a mass over charge equal to 16, and we worked out the mass of the methane molecule. You probably noticed that there was a little tiny peak here at 17. Okay, so this little thing here that has a mass over charge equal to 17, and you might have been going, well, where did that come from? Did we just create matter out of thin air and we made more mass? Well, no. Okay, this has to do, or this peak, which we call an M+1 peak, right? Because it's the parent plus 1. So we say M+1, and then we put radical cation. Okay, where does the +1 come from? It comes from the presence of carbon-13 in the sample. Okay, I don't know if I know you know what an isotope is, right? An isotope is two atoms that are the same, but they just have different numbers of neutrons. Well, you probably remember that the most abundant isotope of carbon is carbon-12. Then we have carbon-13, and then we have carbon-14. Carbon-14, okay. Carbon-12 makes up about 98.1% of carbon, and carbon-13 makes up about 1.1%. And that's where the M+1 peak comes from. It comes from the fact that there's about 1% or 1.1% of carbon-13 in any organic molecule. If you're sitting there going, but yeah, what about carbon-14? carbon-14, my friends, makes up 1, 2, something like that percent. Okay, something, so it's just ignore it completely. But again, if we have an organic molecule with only one carbon, you've got a 1% chance that you have a carbon-13, okay? And so that's going to have a mass that's one heavier than the parent ion. So there you go. That's where it comes from. Okay, it comes from the presence of carbon-13. Let's go back to the pentane. Where was it? Here's my pentane, right? And you can see that I have an M+1 here, right? So I have 5 carbon atoms, so it's what, 1.1% times 5, so I have 5.5% chance of having a carbon-13 in my molecule. And if you go to benzene, well, there's 6 carbons there, so then I have a 6.6% chance of having a carbon-13. So my M+1 peak keeps getting bigger and bigger the more carbons that I have in my molecule. All right, that's the idea. Now, I made a note to myself this morning, okay, that if you're wondering, is there a practice problem where I could try this? The answer is yes, okay? And you would want to look at Skill Builder 14.3. You've been having me for lectures now for 3 weeks, and this is the first time I've actually brought up a specific skill builder. I would like everybody who's hearing the sound of my voice to take a quick peek at Skill Builder 14.3. Now, the next question after you do that problem is you're going to say, well, am I allowed to bring a calculator into the quiz, into quiz 14? And the answer is yes. It's the only quiz you're allowed to bring a calculator into. And then the follow-up question is always, well, what about the final? Because if I'm allowed it on the quiz, I'm allowed it on the final. You won't need it on the final, okay? You will not need it on the final, but you might need it on the quiz. Okay, so you're allowed to use a non-programmable calculator for quiz 14. Everything else, no calculators. You will not need a calculator for anything else, just for this one quiz. All right, so by comparing the heights of the M+1 and the molecular ion, you can estimate how many carbons are in the molecule. And again, you can get some practice on this by trying Skill Builder 14.3, and there's a couple of questions that follow it, and that'll guide you through how to predict the number of carbons based on the height of the M+1 peak. All right. Well, with that in mind, let's move on to section 14.11. If you're wondering about isotopes, if you're thinking, well, carbon-13 is 1% abundant, are there any other isotopes that might be of interest to me as an organic chemistry student? Great question. And there's 2 of them that we're going to look at besides the M+1 that results from carbon-13. And they are chlorine and bromine. Okay, chlorine and bromine are the 2 that you have to know. So let's take a look at them. We're going to look at chlorine first. It's got a lower atomic number. And it turns out that chlorine has 2 abundant isotopes. Okay, 2 isotopes for chlorine. We have chlorine 35 and chlorine 37. The relative abundance of those is 76 to 24%. And so if we run a mass spectrum on something that has chlorine in it, what we're going to see is we're going to get a molecular ion, right? We're going to get the parent ion, but then we're going to get an M+2 resulting from the chlorine 37 isotope, and their relative heights are going to be about 3 to 1. So if we look at this molecule here, this is chlorobenzene. So this is called chlorobenzene. It's got a formula which is C6H5Cl. Could anybody calculate the mass of this compound? I'll give you a second to bust the calculator out. And might have to go back to my notes where I said the chlorine has a mass of 35, right? That's our low resolution mass that we use. Did anybody calculate the mass of this molecule? Anybody? Yes, thanks, Sarah. Yes, its molecular ion should be at 112, okay? Should have a mass over charge of 112. So let's dig in here. So this is 100, this is 105, this is 115. So 111, 112. So this is mass over charge equal to 112. And then we skip 113, it's really small, and then we have something at 114. So this is mass over charge is equal to 114. So what do we know? We know that this first peak is the parent ion, and this second one is M+2, right? 112 plus 2 gives you 114. Now let's look at the relative heights. You can see that the relative height, if we give this a height of about 3, then that would make the height of this about 1. And there we go. So that means that if you look at a mass spectrum and you look on the far right and you see two peaks that are two mass units apart from each other, and they have a relative peak height of 3 to 1, that means you're gonna have bromine in your molecule, or sorry, chlorine in your molecule is what that means. All right. Now, with bromine, you're probably wondering, well, what's the relative abundance of those? Great question. The relative abundance of bromine 79 and bromine 81 is 51 to 49. So it's pretty much 1 to 1. Okay, it's close enough to be 1 to 1. Yes, the molecular ion is going to be a little taller, but not much. And so if we calculate the mass of this compound, so this is C6H5Br. I'll give you a second try and see if you can calculate the mass of this compound. Anybody get the mass of this compound? Bromobenzene. Anybody? So you got 156. Exactly. Thanks, Sarah. It's 156. That's going to be my molecular ion. Well, let's check. So here, this must be a mass overcharge of 156. And we see that we have two peaks that are separated by 2 mass units. They're almost equal in height. So this must be a mass overcharge equal to 158. Right? So this would be my molecular ion, and this is my M+2 molecular ion, right? From the isotope bromine 81. Son of a gun, I didn't mean to do that at all. Oh, sugar, where was I? There's my M+2. And there you have it, my friends. So again, if you look on the far right of your mass spec, you see 2 peaks of relatively equal intensity. That means you're going to have a bromine in your molecule. All right. Well, let's move on and talk about fragments a little bit more. So now we're moving into section 14.12.